I will introduce string theory from the main basic motivations. Why is it a good UV completion of gravity? And then I will also tell you what is this swampland program that is very attractive nowadays for people working in the string phenomenology community. And in particular, because I'm interested in black holes, I will want to focus a lot of this talk on why black holes are interesting to learn about gravitational effective field theories and their relation with a UV complete theory. So why are they a good testing ground for our theories of gravity? And I will leave for the second part of the talk a more technical part where I can tell you a little bit more in details. Part of my recent work that I did while I was at the Max Planck Institute in Munich with a group of Dieter Lust and Nicola Cribiori, Marcus Di Rigle, and Marco Scalisi. And I'm still working with them and with Ivano Basile. Okay, so let me start from something that should be common ground in any case, which is that we all agree that fundamental interactions are described by quantum. So this is like a paradigm that we start our career on. In fact, the great success of quantum field theory, it's been being able to describe fundamental interaction by giving some predictions on experiments that we were able to test. The language of quantum field theory and our predictions is Feynman diagrams. We have tested the theories, quantum field theories at colliders. And so the standard model of particle physics is one of the best prediction or understood sectors of physics and fundamental interaction. So what this has told us is that interactions are mediated by gauge fields, which are spin-1 fields. And matter that interacts consists of either spin-1 half fields and we know now also spin-0 fields. I will completely skip over the problem of dark matter. So there's definitely more matter than we know of, but the one that we can test or we understand very well. There is just one other field that we see in our universe, which is gravity, the gravitational field. Gravity is an interaction that is not covered by standard model. But we know that we can describe gravity through a massless symmetric tensor field, which has two physical polarizations, which is this two index tensor. Alpha came from the index of a coordinate that then got removed. So let's take it as an index of a gauge, a specific gauge for this H-mu tensor. So we know that if we want to extend the standard model to include also fundamental interaction, including gravity, we should find a theory of gravity where the fundamental mediator of gravitational interaction is the spin-2 field. However, as you all know, the main problem is that differently from the case of the standard model interactions, all the divergences in Feynman diagrams that can be reabsorbed through renormalization for standard model interactions cannot be reabsorbed in the case of gravity. Trivially, the interactions diverge just by power counting. And so we face an important no-go in trying to quantize gravity the same way we quantize interactions in the standard. And this seems that we are stuck with this amazing tool, which is quantum theory. And this is a problem because in our universe, we know that there is gravity and it's a dynamical field, and we know everything we've described as a field is quantized. So there's definitely the option, and there's some research that takes into account the possibility that gravity is not a quantum field. But I will take the approach of unifying all the interactions in the same language. And so I want to find a theory that includes that is a consistent theory of gravity, also the quantum level. And there's a caveat. I can get away from these problems by considering not just local interactions, but even the possibility that interactions are not local. And the simplest way to generalize this local interaction is to spread the locality, not just from a point to a line. So instead of having point fields that describe point-like excitations, now I'll have a string that I quantize the same way analogous to what I would do for a field that is local. So the propagation of a string is not a world line, now it's a world sheet. And the interactions between world sheet will be the dynamics of my theory. In this way, what happens is that the divergences that appeared in an interaction of a spin 2 that were local, now they somehow get spread out in this world sheet, and they are not divergent anymore. How do we make contact with the point particle physics that we know and we have tested? Well, if we imagine that these strings live at very high energies, that at low energies, what we see are just the lightest excitations of these quantum strings. And it can be shown that the massless spectrum of these oscillations, that these strings that move on a two-dimensional world surface, world volume, but on a higher dimensional world, that can be our four-dimensional universe, they have in their lightest spectrum the fields that include a spin 2 massless symmetric tensor, which means that we are in the right place to describe gravity at the quantum level. The amazing property of this theory of strings is that it is consistent at every energy, including the Planck scale. So we have found a way by moving from point-particle interaction to string interactions to take into account some fields that behave as point-particle interactions at low energies. But once we include the full description in terms of strings, can be consistently extended to a theory up to the Planck scale. Why is the Planck scale important? Because this is the scale where we would not be able to renormalize our quantum theory. And so we would, the theory would break down. Just a point like gravitational interactions is not consistent anymore. We don't have a theory, we don't have the tools to compute anything at this scale if we're not in string theory. However, why isn't everyone working on string theory? Well, the reason is that there's some pros and cons to these framework. As I said, the string is propagating, describing not just a world line through its evolution, but a world sheet, which is a two-dimensional surface. However, this surface is embedded in what we call the universe target space, which in string theory requires 10 or 11 dimensions to be consistent quantum mechanically, in order not to have anomalies, in order to be well defined. 10 or 11 dimensions is not what we've experienced in our universe so far, so that could be a limitation of the theory. Moreover, I told you at the beginning that the great success of quantum field theory is to be able to give predictions on processes that we can test at colliders. Actually, string theory gives us one example of a UV-complete theory of gravity, but it gives too many examples of possible UV low-energy theories that can be constructed from string theory. So we lose predictive power because we have too many options. Also, in all these options, there seem all these realization of a low-energy universe. There are too many fields, too many particles. We don't see all of them. So until we find all of those or additional particles to the standard model, This seems another problem. In order to be consistent, string theory requires supersymmetry, which is still to be found in colliders, but doesn't mean it's not realized somewhere in the universe. And not all the possible theories can be derived from string theory. Not possible. All the possible effective quantum field theory come from string. So, as I said, in particular, we cannot predict the standard model. However, all these properties that may discourage us from using string theory as a framework also give us a lot of possibilities if we're interested in understanding what is a generic quantum theory of gravity and why it is connected to our universe. It was easy enough to find a way to reduce a 10-dimensional theory to the 4-dimensional world we see. In fact, there's no issue, there's no nothing preventing us from having a smaller compact dimension that we have not been able to see yet at experiments. And so we have to think of this 10 or 11 dimension as the 4-dimensional universe we know, with, in addition, smaller 6 or 5-dimensional, 6 or 7-dimensional compact geometries that are so small that they are not extended. The fact that we have a lot of examples that we can study in string theory also give us many concrete examples that we can one by one study. We can find examples where we have certain gauge fields that we want to check what role they may have in inflationary units. We can have a different kind of vacuum where we can test what kind of dark matter particles we have. So we can really define a playground of effective theories derived from string theory that is always very useful for theorists to play with. And because of supersymmetry, we can actually compute things exactly, because supersymmetry is an important, is a strong constraint on the theory, but the constraint makes a lot of things simpler. It's a simplification. On the case I was mentioning before, we can only derive certain quantum field theories, but we know really well how to construct them. Because of the microscopic ingredients in string theory, consisting both on strings and branes, which are extended hypersurfaces on which open strings end, we have control on the microscopics, and we can use this to engineer quantum field theory with certain properties in higher dimensions, which would be strongly coupled, that maybe don't have a Lagrangian description, but whose symmetries and properties we can grasp from their microscopic construction. So this is also something very powerful that we can do in the framework of strings. But what I will talk to you about in this talk will be how can we address directly questions about the fundamental properties of gravity, especially in quantum regimes, in string theory. There's no other framework where, as I said before, where we can compute things once we go to the Planck scale. We don't have a theory of gravity which is defined at the Planck scale that we can work with, derive things from, other than string theory. There may be other examples that wanted to define a fundamental theory of gravity, but it's really hard to compute things in other settings. So please bear with me the excitement for string theory. There have been already major successes that have justified the continuous work of string theories. Let me mention this because they revolutionized somehow the way we use string theory and the way we think about gravity. There had been in the 70s already some hints that gravity may have a holographic origin. So a gravitational system in a certain volume could be completely characterized by what happens on the surface of this volume. And through string theory and a specific construction, there was a quantitative realization of holography that goes under the name of the SCFT, that I'm sure all of you know. So in a specific example of anti-de Sitter space derived from string theory, there has been a dictionary that tells you how this system is correspondent to conformal field theory at the level of correlation. And this was a first important result that then has led, have paved the way to many studies of how much can we push this duality between gravity and a conformal field theory, or better, how much can we reconstruct the full gravitational universe from properties of the conformal field. How can we understand black hole evaporation, black hole dynamics, using properties of the conformal field theory? And so there's many programs going on interested in this direction. At the level of specifically black hole properties, I told you before, string theory has some microscopic constituents, some microscopic degrees of freedom, which are in addition to the strings that dynamically describe this, their two-dimensional word volume. There's also d-branes, which are non-perturbative objects on which strings can end. And these d-branes can wrap the compact dimensions in such a way that they become point-like when we look at the four-dimensional effective field theory. But they are charged objects that give rise to black hole microstates. They can curve the space, and they can be the constituents of our effective field theory black holes, whose entropy can be recast in terms of these d-brane charges. So string theory explicitly provided evidence for what is the origin of black hole entropy. And so there's not prediction for a specific set of matter fields and gauge fields. There's still a prediction from string theory of important properties of classes of states in the effective field theory. And when I say effective field theory, I'm saying a theory of gravity at low energies that does not need quantum effects taken into account, but needs to be somehow understood as coming from a UV complete theory, and in this case, string theory. The swampland program has taken this prediction of a string theory as a sort of guiding principle. Let's try to understand everything that can be derived from string theories as property of gravity at low energy. The same way as we have understood the black hole entropy in terms of microscopic states coming from string theory. Is there something else that we can say, oh, this is a property of gravity, but it's due to a property of the UV complete? Before I go on, since I will use certain ideas of the black hole metric and their thermodynamics, I want to show you the metric so that it's clear what I'm referring to. The simplest black hole metric is the Schwarzschild metric. This is a space-time. When I say a metric, gravitational system, it's described by configuration in space-time. Flat space is a trivial configuration. It has a flat metric. We can choose our favorite coordinates for it. However, Schwarzschild has a non-trivial metric. This is expressed as a line element. And the radius of the horizon of the black hole is can be seen from this warp function. The important thing is that the moment we try to study quantum fields on top of this non-trivial gravitational background, we see that they perceive a certain temperature, and in such a way that the black hole can be described as a thermodynamic system that satisfies the first law of thermodynamics with a certain temperature, the Hawking temperature, and the Bekenstein-Hawking entropy, which is given by the area of the black hole. And you can define a free energy of the black hole from the partition function of the semi-classical action in the Euclidean space. The Reisner-Nostrom metric, which I will use also later, is the case where we, in addition to the metric of the black hole in the vacuum, we add a gauge field in the picture, and then the black hole can be charged under this gauge field. And what's interesting is that now there is a limit where the mass and the charge of this black hole are equal, where you can see that the temperature goes to 0. So this limit is the extremal limit, and it is interesting because in the extremal limit, these solutions can be solutions that are actually supersymmetric states. And so they have a precise realization in string theory, and so they will be the correct systems to study if I want to study black holes from string theory. And there is a different generalization of these metrics, but those are. So we are now in the framework of having a theory of gravity, which is UV complete, that predicts certain low energy theories. However, the point is that not all the possible low energy effective field theory with gravity or not can be completed back to a string theory. This is the problem of this swampland program. That is what we call the string landscape, which is the set of all the possible low energy theories that are derived from string theory. But we know that there is a large swampland of theories that for some reason have properties that clash with string theory properties. So the question is, given that we have so many effective field theories, that we could even think that string theory can give us any possible low energy, how come that only some classes of them admit a UV completion? Maybe these classes of theories that admit a UV completion are those that have certain properties that can be pinpointed back to UV properties of quantum gravity. Not just properties of string theory, but properties of any quantum theory of gravity. So the idea is, if we study this landscape and the properties of the theories in this landscape, then maybe we can understand properties of quantum properties of gravity that would not be possible to access just from the low energy perspective. Because from the low energy perspective, this swampland and landscape would be the same thing. These are all good effective field theories, but not all of them admit a UV completion in string theory. So the goal would be to develop a set of principles that we can apply in the EFT to discern either if this low energy theory can be completed to a UV theory of gravity, be it string theory or whatever form a generic UV complete theory of gravity has. And why is it possible? How can we get constraints on the low energy theory from the UV? Well, this is due to the UV-IR mixing that happens, and we already know this happens even before string theory, when we deal with an effective field theory and we start including gravity. Let me give you an example. We know the Bekenstein bound. I hope if we don't know, this is the Bekenstein bound. It tells us that in a certain region of space, the entropy, the maximum entropy of quantum fields is bounded by the entropy of a black hole that this is the form of the area of the black hole, and this gives us a bound. The argument for this bound is that actually if the matter, this region of space, would, has bigger entropy than the equivalent black hole, then we could throw more matter in the system dynamically, and then the black hole would form, but then the entropy would decrease, and that's against the second law. But this is interesting, first of all, because it tells us that naively in a QFT, the scaling of the entropy of the QFT with the volume and with the volume and the UV cutoff, this lambda, is cubic. And so somehow the Bekenstein bound is hinting to the fact that the quantum field theory is overcounting the number of fields. But see that this bound is relating the UV and the IR cutoff. In fact, the Bekenstein bound could be naively violated in a QFT. So we need to impose this constraint. And this brings us to a non-trivial constraint on the between lambda and the volume, so or L. Moreover, we need not just to impose this bound, but for this bound to make sense, we need to be able to put energy into a certain volume such that at a certain point, black hole states form. And this is the transition from your QFT without gravity to an EFT that includes gravity. If we assume that at a certain point, including higher and higher energy states, a black hole will form, it means that we're assuming that gravity is present in our full theory. And moreover, in order for this to happen, that the states become black holes, then these states need to be in a volume that is at least as big as their Schwarzschild radius. And so in addition to this bound, we also assume that the Schwarzschild radius is smaller than L, the characteristic length or the UV IR cutoff. And this requirement gives us bound where explicitly we have a bound between a relation between the UV cutoff and the IR cutoff. And notice that this bound makes sense because we have introduced the Planck mass in the game. So we've introduced gravity. Notice that, again, the maximum entropy of states, the QFT, right before they collapse to black hole, goes like area to the 3/4. So we've already reduced the dependence of the maximum entropy of a QFT from the dependence on the volume to the dependence on the area. So we're going towards the holographic prescription idea. Okay, a more concrete bound between UV and IR is the species scale. The presence of light fields in the effective field theory renormalize the Planck mass, the propagator of the graviton, and then the Planck mass gets reduced by factor 1/√n. We can also see it by the evaporation of a black hole, which has a certain global charge with respect to all these particles. And this was studied by Vali and Gavadasi and Porras. And this is a very important bound because when we're dealing with an effective field theory, we assume that we can just take the highest cutoff to be the Planck mass. But if we have a high number of light fields, dynamical fields in our scalars in our theory, then the UV cutoff can actually be reduced consistently. Moreover, this tells us that if we have a parameter space of our EFT that is such that in a certain point there's a tower of fields that become light, an infinite tower of fields that become light, then our quantum gravity cutoff goes to 0. So this is actually a breakdown of the effective field theory. There's been some studies recently that take this species scale more into the string phenomenology approach, and it's possible to get entropy bounds in generic dimensions and generalize these bounds in any possible compactification of string theory, and they all work the same. But let's go more into the black hole story. Black holes can explain many properties that we think are properties of quantum gravity. How do we see that they start telling us that there's some non-trivial dynamics with gravity. Well, for example, I told you that the black hole can be extremal in the case of the presence of gauge fields. Then an extremal black hole somehow has zero temperature. Thermodynamically, black holes decay because space with empty space with gravitons is thermodynamically favored than a finite temperature black hole system. But if the temperature is zero, there's no more thermodynamic process that would lead this extremal black hole to decay. So how does it happen? What happens? We don't see any remnants. The systems seem not to exist. How do we get these how do we ensure that this black hole decay and does disappear from our universe? Well, the first and conjecture that again was part of our literature and scientific knowledge way before the swampland program is the weak gravity conjecture. The weak gravity conjecture is a requirement that in the spectrum of our effective field theory, which could be the standard model even before we couple anything to gravity, there needs to exist a particle whose mass to charge ratio satisfies this bound. And this is such that when we get to extremality, then this particle would be allowed to be emitted, because then it would lead to a black hole state that respects the BPS bound. And depending, if we change our effective field theory, we go from Einstein gravity to higher derivative theories of gravity. We add other perturbation. This bound changes, so it's sensitive to the kind of effective field theory we have. Not only in flat space, but also in the sitter, which is space with positive cosmological constant. There are interesting bounds that we can derive. Sorry, on the low energy spectrum, on the masses of our spin 1/2 fields, or spin 0 fields, that tell that these are sensitive to the dynamics of black holes. Because this bound, that was a Festina lente bound, looked at black holes in the sitter space. And in the sitter, in addition to the extremal black holes, extremal black hole line, there is, since there are also in the game the cosmological horizon, there's a phase space that it's cut and it looks like a shark fin. It is people, these people asked if what happens if a black hole evaporates by going outside, outside of the phase space. And they found that falling out of this fin would lead to a crunching spacetime. And in order to prevent that they derived a bound on the possible particles that are emitted in the evaporation of the black hole. So this is another issue that comes when one includes the dynamics of black holes in our effective. One of the most important properties that we think belongs to a quantum theory of gravity is the absence of global symmetry. And this is also related to the dynamics of black holes in just gravity. In fact, we know that black holes evaporate, as I just told you, they have to emit mass and charge. And however, if the charge is due to a gauge charge, then because of the presence of gauge fields in the theory, then the evaporation of charged particles has to satisfy some charge conservation. But if the charge is global, we can throw charges into the black hole. And in the evaporation, there's nothing ensures that this conservation of charge will be preserved. We could have remnants of just global charge, or just global charge could be destroyed. So there must be something that in the coupling of effective field theories, the UV, gravity in the UV, changes this global symmetry either by breaking them or gauging. And this is significant also for our world because in the standard model, we know there are global symmetries, and eventually in a UV complete theory of gravity, these symmetries should be broken. Recently, there's been important developments that have led to identify generalized global symmetry. Namely, there can be global symmetries due to charged operators that are not just, there are P forms, there are forms of any rank due to non-local operators. And So not only we need to ensure that zero form symmetries, global symmetries are gauged in the UV, but that any for higher form symmetries cannot be global and preserved in the UV. This has been dubbed cobordism conjecture, namely the requirement that if we have a low energy effective theory that comes from string theory, so we've compactified this in an internal geometry, then there are important properties of the internal geometries such that they need to be to have a trivial cobordism in order to avoid the having a conserved E minus K minus 1 form global symmetry for a K cobordism. So the ramifications of these simple properties like the absence of global symmetry in quantum gravity go deeper into the properties of string theory effective theories. Let's go to now to for the last few minutes to telling you how do we work with this in practice. Let's talk about specific black hole examples. I'm working with an effective Lagrangian. This is an n equal to 2 supergravity Lagrangian. This is the bosonic part. I am missing all the fermions. The reason is that I want to study black hole solutions, effective field theory, and I want to study configurations which have zero fermionic fields. So because of the structure of the theory, when I derive equations of motion, the fermionic equations of motion and the fermionic field can be decoupled. And so black holes are simply solutions of these bosonic actions. What's important to notice here is that why is this low energy effective theory of coming from string theory? There are, what's in this? There is Einstein-Hilbert term. This is a 4-dimensional action. It means that this is a 4-dimensional Einstein-Hilbert term. This is the 4-dimensional space that I suppose we live in. All these fields come from the choice of the internal 6-dimensional space. I decide to compactify, make compact 6 dimensions. So I've chosen a certain geometry. In order for this theory to be n equal to 2, when there is no scalar potential, then I have a Calabi-Yau internal manifold, which is interesting because it's described by few algebraic properties, and that they can be collected in scalar fields that are described in a linear sigma model, and additional U1 gauge fields. So my black hole will be a kind of Reisner-Nordstrom black hole because there are gauge fields in the game, but not just one. There are many. My black hole will have many electric charges, many magnetic charges. On top of that, it can be coupled to scalar fields. So it's a little bit more complicated than the Reisner-Nordstrom I showed you, but this complication actually enriches the properties I can study. In fact, I told you at the beginning that the black hole has a certain temperature and a certain entropy in general. Now, this entropy and the temperature can go from, they take real values. So I can try to study if something interesting is happening at the limit of 0 or infinite temperature and entropy. And in fact, it's possible to define a certain distance related to the black hole metric, which was known already at the time of the Witte, which is a metric distance. It's been used in the context of the swampland because the temperature and the entropy are expressed in terms of black hole quantities. And in particular, they can be traced back to also the scalar fields. And in string theory, the scalars are basically the parameters of the moduli space of our effective field. And these moduli space have the property that if we move in an infinite distance in this moduli space, we are reaching the breakdown of our theory. And this has been quantified theory in the sense that it's always possible to show, in the example studied, that, and this is a conjecture, that if we go at infinite distance if we move an infinite distance moduli space, there is a set an infinite tower of scalar fields that become massless exponentially in distance on the moduli space. So whenever we find this infinite distance in moduli space, we know that we are breaking down, the effective field theory breaks down, which means that if we're reaching a theory at infinite distance in moduli space, then we're going from the landscape to the swamp. So we have a criterion that tells us that now we've reached an effective field theory that is not more compatible with the quantum theory of gravity. Notice that any distance or any phenomenon that we want to relate to a breakdown of the effective field theory from going from the landscape to the swampland must be a criterion that is related to the coupling of the theory to gravity. So this criterion should become trivial when we send the Planck length to zero or the Planck mass to infinity, because it needs to be intrinsically a criterion that only comes into account when we couple our theory to gravity. So what we did was take into account the black hole solutions that I was telling you. Well, this was just a comment on possible different definitions of distance, and try to study distances in temperature and entropy, because they have to do with black holes, and the black holes are coupled to scalar fields, and so maybe they also are related to the distance in moduli space. And let me mention that these distance in terms of temperature or entropy are actually interesting, because if you look at the systems at finite temperature, just generic systems at finite temperature, then we know that there are Matsubara frequencies that are related to the temperature. And in fact, these frequencies may be associated with the tower of states that become light when we go at infinite temperature. And together with these Matsubara modes, we can assume to have a dual tower of winding modes in the Euclidean thermal circle. So somehow this is just to say that the temperature seems to be an interesting parameter in our system. So we can, I just told you this is true for generic systems. We want to study gravitational systems. So let's look into something related to spacetime. So the easiest example would be to study the Unruh temperature. We are still in, let's say, we don't need to introduce gravity. We're in flat space. Nothing is curving our spacetime, but we can change system of coordinates. We can go into an accelerated observer. This means that we're describing our flat spacetime in terms of these parameters. This is our world line. And then in these coordinates, it looks like we are having thermal state. And this thermal state has an associated thermal entropy, which is called Unruh. This is the Unruh effect. However, this does not depend at all on Planck length. So Unruh has nothing to do with swampland. It's nothing to do with the criteria about gravity. We really need to go to a non-trivial gravitational system. So let's go back to our black hole. Well, the temperature of Schwarzschild, of course, has dependence on the Planck length. And analogously to what we called Matsubara frequencies, now there are Hawking frequencies, Hawking modes. And these modes could parameterize towers of fields that become massless in infinite distance in parameter space. And the distance of associated with these black holes is analogously to what I wrote before, the modulus of this logarithm. However, for Schwarzschild, the temperature and the entropy are both expressed by one parameter. The mass of the black hole governs all the properties of the Schwarzschild black hole. So we're still not able to test different directions, time and temperature and entropy phase space. So we move on to the Reissner-Nordstrom black hole, where we have two independent parameters, M and Q. So in general, we consider the non-extremal case, where entropy and temperature are related by these interesting relation. S times T for a Reissner-Nordstrom black hole is equal to constant, to a non-extremality parameter. And we could, in principle, vary S and T in such a way that C remains constant. And the associated Hawking modes are given by this expression. And again, they decouple, of course, when the Planck length goes to zero. So we are in a safe gravitational system, and we can try to say something that is relevant for the coupling of our effective theory to UV theory of gravity. Sorry. Now, we are going to have another slight generalization, which is the case that I was telling you about, the n equal to 2 black holes. The thermodynamics is very similar to the one of Rice and Nostrom, except that now quantities will be addressed with certain parameters that come from the coupling of the scalar field. Let me give you one simple example, which is the case of Einstein-Maxwell-Diraton, where you just have one field, but this is just one case of the n equal to 2 matter coupled supergravity. So let's just stick to one field. Things happen the same. This is just to say that we can capture in this analysis more general black holes that come from string theory. This is the phase space. The entropy and temperature parameterize all the possible solutions that I have. This blue line is Schwarzschild. This is the case where in our solution, I set the charge to 0. The red line is the C equal constant line. So I could move in parameter space keeping C constant, but I will hit the Schwarzschild line at some point. And so this part here is outside of the phase space. So the question was, can we see some of these distance in the phase space S and T? You can see that there's a space here to follow this line inside of solutions, of black hole solutions inside inside this graph, going at infinite temperature, so entropy or infinite temperature. Or I can go to 0 entropy and zero temperature and 0 entropy, sorry. Is this related at all to infinite distance in moduli space? Am I following directions or trajectories that lead me to the breakdown of the EFT? This was the question that we were trying to address. We took a particular model in order to be able to get a concrete expression for the entropy and the temperature. We need to have an explicit example for expression for these quantities, this coupling I and R, which depend on the scalar fields, and the metric Gij of the nonlinear sigma model. So here I'm specifying a nonlinear sigma model this way. The electric and magnetic charges of the black hole are given by the gauge fields and this combination. The extrema ones are important because, as I said, they preserve some supersymmetry, and they can be obtained with an extremization procedure that goes under the name of attractor equations that have been studied a lot in the past, and they are at the core of understanding the structure of BPS states in string theory. But here, this was just to give the equations for reference that lead me to this definition, which is I can define volume of the 6-dimensional manifold I have compactified on. And this volume depends on the scalar field. So here is the first dependence on the scalar field. In this model I was studying, there's only 3 scalars. So the product is sometimes called STU. But this volume sets the scale of the Kaluza-Klein masses and inversely of the winding. These masses become light when the volume becomes light or where the volume becomes big. So the distance in moduli space can be defined in terms of this volume. Infinite volume distance means Kaluza-Klein masses becoming light, and 0 volume means a winding mode becoming light, which, because there's a logarithm, there's a modulus and logarithm, they're all infinite. This is the explicit metric of the black hole. The entropy and the temperature have this expression, and you can check that they satisfy S times T equals C, the non-extremality parameter. All these parameters, they are just rewriting that depends on the volume at infinity and the charges of the black hole. And so, because of the structure of the metric, what's happening to the scalars is that they are fixed. They depend on the charges and the moduli at infinity. In such a way that I can write the volume of the 6-dimensional manifold that depends on the scalars at the infinity, and I just call it the infinity, or at the horizon. And the volume at the horizon that depends on the scalar field is given by the entropy, the temperature, and the charges of the black hole. So this is the relation, the key relation that connects my black hole solution that is given by a certain charge and temperature and entropy to the value of the scalar field. So if I want to know where I'm going in the moduli space, if I'm going at infinite distance, I need to see, or I can see what happens when I tune this quantity at the 0 temperature, 0 entropy, by varying the charges of the black. So in this case, there is electric charges and the magnetic charges, and I've chosen to fix Q0. So I will move in the phase space S and T, keeping Q0 fixed. It's not limitation. You can do the same thing, keeping P fixed, the magnetic charge fixed. So what happens is I can follow this image in different limits, and I can reach, as I was saying earlier, the limit of infinite entropy, infinite temperature, or 0 entropy. What happens to the volume in these limits? Let's take, for example, this limit where I go to a 0 temperature but finite entropy. Unless one follows a particular parabola, for which I need a dedicated discussion, a slightly different discussion, but the result is the same. Taking this expression of the volume of the internal manifold as I reach the horizon of the black hole, this volume goes to 0 when the temperature goes to 0 at fixed entropy. This means that the Kaluza-Klein masses goes to infinity, but it means that the winding modes go to 0. In region 1, T goes to infinity. This is the same expression of for this volume that depends on the scalar field, and this goes to infinity. So now the Kaluza-Klein modes become massless. So this is a relation between these phase space limits and the limits of our effective and the breakdown of our effective. In this case, for example, you can see that what's happening at infinite temperature is that there's a decompactification of the internal manifold. The region 3 is the region where there are small black holes, so they have 0 temperature and 0 entropy. Oh, sorry. Okay. The different limit, just to tell you for completeness, I can do the same thing by looking what happens at varying the entropy. And analogously, there are a region where the Kaluza-Klein modes become light. And what happens when the entropy goes to 0, however, it's that it means that the horizon of the black hole is becoming small. If the horizon of the black hole is becoming small, it means that I'm reaching a regime where my states become almost the size of a string. So we expect that the breakdown that's happening in this case is that I need to take into account stringy states. So I'm leaving the supergravity effective action, that is an action for point particles, and I need to take into account other stringy states. And this is, people know how to do it by introducing alpha prime corrections and higher derivatives in the n equal to 2 supergravity action. Okay. I'm almost done, I think. Antonio, I have 5 more minutes.
Yeah, you have more time. We have some flexibility.
Okay, thank you. Yeah, this was just a comment that on this part. We can reach different kind of states by moving around in this plane, tuning the charges of the black hole. We can interpret certain limits in terms of string theory states that come into the game. And there is an interesting fact that happens when we are in the extremal limit on this line. because there's zero entropy but finite temperature. And these states had been studied already by Hosny and Wilczek in '92, and they seem to be maybe related to string states, but there's interesting things happening also at a very high temperature, that may be some stringy black hole transition. And so this seems some interesting limits that could be analyzed. Let me not forget to mention that actually once we know that there's some string state that should be taken into account, we need to look at the compactification explicitly, because there could be other state, not just the string states. There could be de Broglie states that break down even before we reach the decompactification scale. So let's say these are necessary but not sufficient constraints on the breakdown of the EFT. Maybe I said it the opposite. One interesting comment is that these limits may reflect also on the coupling gauge coupling of the theory. In fact, recall this is the piece of the Lagrangian of n equal to 2 supergravity that describes the Maxwell fields. And we can look, for example, at one of them, the graviphoton direction, the 0, 0 direction. And if you write explicitly this coupling, this is also given by the volume. But this coupling is the coupling of the gauge field. If this volume goes to 0, it's like the infinite, it's like an infinite gauge coupling, because this is g to the minus 2, and vice versa. If this goes to infinity, then we're sending the gauge coupling to 0. So somehow these limits in parameter space, they're also related to the presence of a global symmetry that's being. So the masses, the towers of fields that become massless, are also related to restoration of some global symmetry. So we're breaking the effective field theory. We're going out of the validity of the effective field theory, because somehow we're recovering a global symmetry that is not compatible with UV quantum gravity. And there's a work in progress with Ivano Vasile is trying to study how black hole states break the global 1,4 symmetries that are associated to any abelian fields in n equal to 2 supergravity. They should break them, and there are some the masses of these BPS states can quantify how much the one form symmetry is broken in the string theory. I left some additional part, but it's very technical. So since I'm already 1 hour in, I could skip it. Let me just say that the punchline of it, I'm finding this relation with swampland conjectures. For example, these I am surveying the phase space of these black hole solutions and looking at these limits, trying to find similarities and analogies with the limits in moduli space that, because of the swampland conjecture, have tell me that there's a breakdown of the EFT in the infinite distance league. I'm also finding a relation with the restoration of global symmetries when there's towers of light states, states becoming light. Is it surprising? Actually, these black holes come from compactifications of string states. So maybe these, the fact that I'm finding these properties is linked or is related to other conjectures that comes directly from string theory without going through the black hole case. And this was our idea. And in fact, I showed you at the beginning that the supergravity action could have a term that was a scalar potential. This scalar potential is a potential that is, I wrote it in the case of n equal to 2 supergravity. But in n equal to 1 supergravity, this potential is written in this way in terms of a superpotential, and gives me possible vacua, including the Sitter vacuum. In the case of black holes, this potential gives me the black hole area and the entropy. Moreover, there's more relations between n equal to 1 and n equal to 2 supergravity. In n equal to 1, we study vacua, like de Sitter vacua, and in n equal to 2, I've showed you the black hole. The couplings are very similar. In the gravitini, which are the spin-free half field of supergravity, are coupled to the gauge fields through the same matrix of couplings, I, this curly I. The same way as the entropy of an electrically charged black hole is given by the combination of the black hole electric charges contracted with the same coupling. And the vacua of n equal to 1 and the black holes of n equal to 2 are obtained analogously via an extremization condition. So there's this hint that we could relate the role of the central charge of a black hole with the mass of the gravitino and the black hole potential, so its entropy, to the n equal 1 gauge potential. There's an issue of having to stabilize all the moduli, but basically these, in order to test if this analogy is consistent, we should have some distance conjecture realized when we express things in terms of the black hole entropy or in terms of the cosmological constant. Because in both cases, we are dealing with the scalar potential, the central charge or the super. And I just show you this part. What are these two conjectures that should be realized analogously and in the same way? One is the anti-de Sitter distance conjecture, and the other is this black hole entropy distance conjecture, the one that I just explained in terms of black holes. The ADS distance conjecture tells us that if we have the anti-de Sitter space, then a solution, a vacuum that has flat space, so zero cosmological constant, is at infinite distance from our anti-de Sitter space. So these moving in parameter space from a non-zero cosmological constant to a zero cosmological constant implies that we have an infinite tower of states becoming light. So our cutoff goes 0 and we are out of the effective field theory, a consistent effective field theory of gravity. In order to show that this actually happens, we had to be careful and make sure that we were in a compactification where all the moduli were stabilized. And in order to do that, we needed to work with geometric fluxes, which is just a caveat for the compactification. But all I'm saying is that it was not trivial, but with the correct compactification where all the moduli are stabilized, which is the case where this ADS distance conjecture applies, then it's shown that both the behavior of the entropy and the behavior of the cosmological constant are consistent. When Q goes to infinity, the volume goes to infinity and the cosmological constant goes to infinity. So the entropy goes to infinity and the cosmological constant goes to infinity, exactly as these conjectures were predicted. It seems that the ADS distance conjecture is preserved in anti-de Sitter, where fluxes and charges are balanced, but I don't want to go into those details. I think it's time for me to conclude, and then if you have some questions, I'm happy to go more into other details during the questions. My goal was to somehow share my enthusiasm towards studying black hole systems in the context of string theory, because, or in general, black holes are our favorite theoretical laboratory where to ask questions about properties of quantum gravity. In the particular case I was presenting here, I was focusing on black holes states that come from string theory. I was studying entropy and temperature and how these the phase space and the infinite distances phase space can be linked to towers of massless states that are appearing in the regions of moduli space. And these can be, if one wants to be provocative, can even call it a temperature distance conjecture in addition to the entropy distance conjecture. One can relate his behavior to just something more fundamental that happens in effective field theory of string theory by seeing a certain similarity between the n equal to 1 case and the ADS distance conjecture and the black hole distance conjecture in n equal to 2. But I think that overall, the lesson that we should learn here is that there are some interesting properties that we see in string theory compactifications that are easily tractable in the effective field theory, and they come from important properties in quantum gravity. So there's still a lot that can be understood and can be studied. I'm also looking into formalizing this distance in moduli space in the case of Calabi-Yau compactifications and black hole states using what's called mixed odd structures. But this is my personal taste. But in general, I think it's a very interesting line of research, and I hope I could transmit some of the enthusiasm to you. So thank you very much.
Thank you very much, Alessandra, for the very nice and complete talk. Question from the audience? Any questions?
Sorry, I
Alessandra,
was over time.
this relation for this mass of this Kaluza-Klein state, this depend on the on the geometry, for example, or this on the geometry that you choose for in your for the metric, or this is independently. There is, and
The specific
behavior,
form is
the specific behavior. Yes.
it depends on this choice. This is basically a choice of the geometry, internal geometry that I choose, but I can generalize this slightly to so-called cubic geometries, where I have more generic combination of 3 x's here, but all symmetric. And in all those cases, these black holes behave the same. But it's true that I would have a slightly different expression for this V. But they will all have these kind of solutions in phase space where I can fix Q0 and look at magnetic charges. So it's a more general class of solutions.
They are more general class. I was wondering if there should not be an extra, there can be an extra parameter for the mass of this Kaluza-Klein state, because you were mentioned that in the limit where these Kaluza-Klein states are massless, there should be some global symmetry of the theory. So there should be maybe some parameter in which in the limit where this that parameterize the breaking of that symmetry, and in the limit when this goes to 0, the mass of the Kaluza-Klein state goes to 0, or you're missing something?
Yes. No, it's the same. So the masses goes to 0 when the global symmetry is where the gauge coupling goes to 0. So there's it's consistent with the fact that when these Kaluza-Klein states become massless, you are at your effective theory breaks down.
So it will be associated with the gauge coupling of this U1 symmetry. In this limit where the U1 gauge coupling goes to 0, also this Kaluza-Klein mass goes to 0 as well.
Yes, because it's the same V.
I go with this B G divided by the total volume. The Q divided by the total volume for this Kaluza-Klein mass.
Yes.
I mean this.
But Q was fixed in my limit.
I see.
This Q0 somehow in this limit is kept fixed, and it's enough to show that there is a limit where I can tell you that you're out of the validity of your theory. I'm finding one limit where you can follow the breakdown of the EFT due to these Kaluza-Klein masses.
But this will correspond to the lightest state, because in principle, for the second and the third excitation, maybe the expression will be a bit more complicated.
But they will all be proportional to V, so they will all be becoming light.
So the expression, yes, the complicated, the general expression for the n mod will be maybe more complicated. Maybe some, I don't know, some Bessel function, because
of what? Sorry, of
because the metric, but the metric is different than it's very completely different than this London syndrome. So in principle, yes,
Yeah,
will
it's
be
really a product, and this volume is the overall. Okay, I think I've missed Antonio. Antonio, sorry, I had lost you.
no, yes, there is some, sorry, there is some internet connection problem. So I think this is for the lightest, for the lightest state, I suppose, because for the general excitation mode, there will be some independence, I think. So
Yes, but this is really like it's a decompactification limit in the end when this volume goes to infinity. So the whole tower become massless, right?
I see.
So there will be like an overall factor in front of all these Bessel functions and all the higher modes. But also let me maybe comment on the fact, because you said, you asked if there was another parameter. These theories are very simple because these are the so-called engaged supergravities. And so this is their action. And in the case without the potential in Minkowski space, there's really like only these couplings, I and R, govern basically the whole geometric dynamics. So it could be that like it's too simple to have a different parameter that you can tune for the gauge coupling and for the and for the for the black hole charges, while you could consider more refined theories where like you have also hypermultiplets and you have gaugings, and so you can have anti-de Sitter solutions with more fields which are coupled and some other fields which are charged in the spectrum and in the solution. But in those cases, it's really hard to find the BPS states or classes of BPS states. And so we did the analysis in this case where you can actually have a modular space and where it's simpler. So it's, that was just a comment.
Thank you, Alessandra. I had another question. Do you get some constraint from this lambda coupling of the dilaton?
No,
Or you
this
keep
is
it as a free parameter?
it's the same. It's the same. You keep it. I keep it fixed. It's you can choose it, and depending on how you choose it, you can describe um, like a theory that comes from the heterotic or other kind of theories, or just Einstein-Maxwell dilaton. It's a coupling that comes from string theory, and depending on how you do your reduction, this coupling can have a different numerical factor. That's it.
And which are the most motivated choice for this, for the value for this
Like square
coupling?
root of 3, for example, or 1/2.
Absolutely.
Yeah,
See.
it's something like
More,
this.
or the unity. So it has to be not so far from unity, not so much smaller
No,
than unity.
exactly. No. It's, and yeah,
Mm,
they just have a different behavior in terms of the charges. So it's interesting to study different kind of examples here. I wrote mostly one because it can be generalized and is less trivial than having just one field. But the expression of the volume, for example, in this case is Q0 over S, and here S is Q0 times P cube. But if you do the Einstein-Maxwell dilaton case, this would be S would be Q0 times P0. So it changes some expressions, but not the functional behavior and the analysis. So it holds for a lot of examples.
Thank you, Alessandra. More
Thanks to
questions
you,
from the
Antonio.
audience? Mm, More questions from the audience? If there are no more questions, we send Alessandra for the very nice talk, and we meet at the next seminar. Thank you so much, Alessandra, for the very
Thanks
nice
to you,
talk.
Antonio. It was very nice talking to you and presenting. See you hopefully soon, and I'll ask you about this biannual conference you told me that there is next January.
Perfect, yes. As soon as
Thank you very much.
still have not been fixed the day, but as soon as
No.
this day get established by the group, we'll let you know.
No, but also like if you are around Padova and you want to stop a visit during your next trips to Europe, let us know.
Thank you so much, Alessandra.
Have a nice day.
Have a nice
Bye.
day.
Thank you.
Bye. Thanks to you.
Bye. Thank you. Bye.